Okay.
Right now, 190 candidates are there. We can wait for a few minutes.
Yes. good afternoon, everyone. This is the last day of the FTP on quantum communication, and especially, the intended speaker, due to some we could not schedule the talks, but we are grateful to Professor Ashwath Babu from IIIT Dharwad, who has already taken in this FDP. And today he's going to talk about quantum error correction. We are glad to have you again here. So over to you. You may take the control of the session. Thank you.
Thank you, Dr. Rajendra. Yeah. So there are 263 participants. Okay. Fine. Okay. So yeah, let me see the charts. Is there any specific thing, questions or anything? Right. Good afternoon to everyone. So yeah, once again, let me thank Dr. Rajendra for inviting me to take one more session for this QT-06. So when he asked me to take a session on quantum key distribution, so I saw the schedule which is being already covered, and so I thought what is not covered, if I can uh, uh, if I can introduce that, that would be more complete. So I requested him to allow me to discuss about quantum error correction. So he agreed. So thanks for that once again to Dr. Rajendra for that. Okay, so right, so we will do that. I'm not sure whether you have come across quantum error correction earlier. Okay, if it is done earlier, then you can treat this as some kind of a revision or some kind of a spin-off from a physicist point of view. Okay, so that is what I would like to bring in. Okay, so right, so I'll use both my hand notes, this whiteboard as well as the PPT. Okay, accordingly, wherever needed, I will use the notes and use the PPT. Okay, right? Yeah. If there is any question, anything you have not understood, please you can just put a message. I'm just seeing the messages also, the chat message also parallelly. I'll stop and I will just discuss. Okay, right? So quantum error correction. Okay, so this is the topic I would like to discuss. Right. So since I have a PPT, okay, let me quickly show you that, and wherever needed, I'll just use my notes. Okay, right. So the first of all, the question is, why do we need to do the error correction? Okay, right. So the question is why you need error correction. Okay, the simple answer, straightaway answer is there are errors. Due to that, the errors need to be corrected. Okay, a counter question you can ask is, why don't we do error-free computation? Why not error-free computation? But the problem there is, okay, as of our technology status, we can't have a pure quantum qubits which are noise free. Okay, right? So answer to this question again, as of now, we don't have, okay, noise free, absolutely noise free qubits. Okay, if the qubits are there by some means, they might have some chances of getting affected by environment, and they may spoil the computation. Okay, so that is why we have to do the quantum error correction. Now, what are those errors? What are the sources of errors? If you can ask, okay. So let me see, I have listed few here, okay, right? So what I have listed is there is something called a decoherence, okay. I'll explain what is a decoherence, right? There is something called gate errors. There is something called crosstalk. There is something called T1 and T2 relaxation. Okay. There is something called control line noise, right? There is something called the initialization error and thermal noise. So these are the only few very dominant error, like dominant factors which are going to induce the errors in the computation. Okay, right? So, right, just a minute. Okay, sorry. Fine. So, yeah, right. Let's understand what is this errors are in the first place. Decoherence, right? So, I intend the system to be in sync with my requirement. Okay, that's the simplest answer. For example, let's say some 10 people dancing on a stage. Everybody is in sync. Okay, if some of the people are going out of the sync, then it would not look appealing for us. So we want everything to be in sync. When I'm talking about one qubit or one qubit state, I'm realizing, which means I'm talking about collection of some qubits. So like ensemble of qubits supposed to be in that particular state. Okay. Or I presume that there is a quantum qubit supposed to be in a certain state to a certain time, but it is not because of the error. So that is the decoherence. Something going out of our coherence requirement is the decoherence. Okay, right? So the gate errors. What are the gate errors? Gate errors means I intend to prepare. Okay, I intend to prepare, let's say, IX gate. Okay, IX gate I want to prepare. Or I want to prepare a Hadamard gate. Okay, but the problem is there is a Hadamard gate supposed to create a equal superposition. After a information, let's say 0 gate go through Hadamard gate, supposed to give me equal superposition like this. Okay, 50-50. But by problem in the gate or some errors in the gate preparation, it is going to give me, for example, it is going to give me, let's say, 49% of 0, 51% of 1. It is close to 50-50, but slightly error. Okay, when it comes to computation, that is also a big matter. Okay, so there may be a gate errors. Sometimes there are two qubits supposed not to interact. Okay, for example, if I just take a qubit architecture, I'll have qubit 1, qubit 2, qubit 3, qubit 4 are all connected. So qubit 1 and 3 are not connected, qubit 2 and 4 are not connected. So that is how I intended to do. I don't want that qubit 1 and 3 interacting. Okay, if there is any interaction, it has to go through the other qubit. Okay, that is what I meant. And whenever I need an interaction between 1 and 3, I do a swap between 2 and 3 and then I do the operation. That is what my strategy. But the problem here is sometimes Q1, Q3 do a cross talking because they're existing very close to each other. The signal from Q1 may go and affect the Q3 status. That is going to create a noise. Okay, so that is the crosstalk between qubits. Okay, and there is something called you are intend to prepare a particular qubit initialization, but you will not succeed in that because of the your preparation faults, your preparation gate faults. So that is the initialization problems. Okay, right? So there is a readout error, just opposite to the preparation. You are going to read, if you are going to read out the signal coming out from the gate, there also you may made a mistake after the measurement, or your measurement gate has some issue, or your measurement process. There is something called a readout ions being used in the case of rare earth ion quantum computing. Okay, there, to read a quantum state of a particular qubit, there is some kind of a readout probe that is also made up of another qubit. Okay, it is so delicate, it just go very close to the actual qubit, and just gets the essence of the actual qubit, and depend, it will not disturb the actual qubit by any means. So in that way, what happens, the information of the actual qubit could be extracted from the readout probe, but the problem is there may be issues with the readout probe, so that may cause the errors. Okay, and the very important thing is T1, T2 relaxation errors. What is this? In fact, this is actually going to give the decoherence. In fact, okay, there is no need to put separately. Okay, there is no need to put separately. But anyway, I have put separately. So, what is the decoherence? What is a T1, T2 relaxation? Okay, let me use. Okay, let me use my hand note and explain. Okay, right? So let's take a simple two-level atomic system. Again, 0 and 1. What I mean by two-level atomic system is, I'll take an atom, nucleus is there, and it has a ground state atom. It has an excited state orbit. Okay. So I take only a snapshot of it every time I don't want to draw. Now I took that snapshot, 0 and 1. Now let's say electron is in the ground. If I supply a photon of energy having energy exactly equal to separation between these 0 and 1 orbits, what happens? The electron may jump to the excited state, okay, and it stays there for 1 microsecond. Okay, it stays there for 1 microsecond. That is the average lifetime of a excited electron. Now, it's supposed to there at that excited state for 1 microsecond. But what happens due to some errors, okay, due to the problem with the surrounding or due to energy, unnecessary heat, it just decays back to ground even before. So what happens? There is a less time for me to do some computation, because the computation is needed a superposition, by the way. But that is a secondary. First of all, I intend to keep that for 1 microsecond at the top, so that by the time it comes back, I will send one more photon. Okay, and then I put the electron in the superposition. What is that? It is superposition trick. So how they realize superposition? Okay, they take electron in the ground. Okay, they send one photon. It puts in 1 microsecond, it stays there. By the time it comes back, you send one more photon which is placed 1 microsecond apart. Now second photon comes, again pushes back. So literally what the electron is doing, it is doing hopping between ground and excited. It's not traveling between the ground and excited. It is like it just disappears from the ground, comes in the excited, disappears from the excited, comes. So literally it is like hopping between 0 and 1. So this is what the superposition is. How it becomes superposition? When I make a measurement of 100 times on this, some specific number of times it in the ground state, specific number of times in the excited state. This is what I create a superposition by sending a sequence of photons placed nicely 1 microsecond apart. So what is this set of photons? This is actually a called pi by 2 pulse. pi by 2 pulse. Okay. So why it is called pi by 2 pulse is, if you recall back your block sphere, which is, okay, block sphere is like this. Okay, so there is a equatorial plane, there is a quantum state representation, makes an angle theta with the x-axis, its shadow makes angle phi with the x-axis. Okay, with the z-axis it makes angle theta. I'm sorry, earlier I said x-axis. Okay, so now a quantum state is represented as cos theta by 2 0 cat exponential I phi sin theta by 2 1 cat. This is alpha, this is beta. Okay, so this is how geometrically you can represent a quantum state on a block sphere, a surface of a block sphere. Now, when a quantum state is along the x-axis, sorry, z-axis, which is quantum state being 0. Okay. Now I want to put that into superposition, means I have to rotate that quantum state either along I should bring into the equatorial plane or any plane other than north and south pole single points. Okay. So that is what the south pole is 1 ket, north pole is 0 ket. Any other point is a superposition. That's what I want to do. So equal superposition, let's say I want to create. So in that case, I have to rotate the quantum state from north pole to equatorial plane. Let's say along the x-axis, I want to put. So about the y-axis, you have to rotate that quantum state. Okay, so it has to rotate it. So to rotate, how much angle I have to rotate? Pi by 2. Pi by 2 angle I have to rotate. So which is done by in quantum gates by Hadamard gate. Hadamard gate does the rotation of quantum state 0 to equal superposition like this. Okay. So which is like rotating a quantum state from north pole to equatorial plane. Okay. So interestingly, in the experimental lab, the Hadamard gate operation is nothing but sending a pi by 2 pulse onto atom or an electron which is in the ground, which becomes a superposition the moment it interacts with the pulse. For some time, for that pulse interaction time, it is going to exist in superposition. Okay. Now, the coming back to T1 and T2, right? So what is T1 is the amount of time it exists in the excited state. So this is an excited state lifetime. Okay. Now the problem is if excited lifetime is less than what is the supposed to, which means the system is decaying much before I want to do the computation. So it decays with the rate of 1 by T1. Okay. So if it is T1 is less than 1 microsecond, then I am in trouble. My computation may go in trouble because I intend to create a pulse with a photon separated by 1 microsecond apart. Okay. If the system behaving as per its own interest, then my pulse would not work and my pulse cannot create a superposition. So that's why T1 error may come if the system decays to the ground state from the excited state well before it's supposed to exist in excited state. Okay, right? There is one more error is T2 relaxation. So other one is T2 relaxation. What is this is? Okay, just to take a real world example. Okay, classical example. Just take a classical example. Or tossing a coin. Okay, if you toss a coin during the flight, if you see the coin, okay, during the flight, a coin is tossed during the flight. You see, coin has a possibility to exist in both head and tail at the same time, okay, during the flight. So I'm talking about during the flight, if something exists in both the forms. So if I put the electron in the superposition state of ground and excited, so it is hopping between ground and excited continuously. Okay. So what it does, it is doing an oscillation in time. What is the oscillations in time? It is going from 0 to 1, 0 to 1, and 0 to 1. It is doing the oscillations. Okay. So, like literally saying the oscillations cannot work forever. How much energy I have given with a pulse, that much time only the pulsation will happen. After that, what happens? The photon, sorry, the what happens? The oscillations decay, slowly decay, because there is no more energy. It will not oscillate and comes back. Okay, so for me, the amount of time the oscillations exist is, let's say, T2. Okay, that is actually called the polarization time. Means the electron being polarized from ground to excited and creating some kind of a dipole moment for some time, no dipole moment for some time. That is how it's a polarization word is coming. So within the time T2, it is existing in superposition. Later what happens, it is may stable down to either one of the state, maybe ground state. But the problem is, due to the environment, what happens? Things may, like a T2 may be shortened, or we say the oscillations gets relaxed even before they're supposed to exist in the oscillation form. So there is a T2 relaxation error. So people call T1 as, okay, T1 as longitudinal error, longitudinal relaxation, T2 as transverse relaxation. Okay, so this is what the actually this both together creates a coherence problem. The system supposed to exist as per my wish to do the computation, that is not going to happen because of the environment or surrounding coming and fiddling with this T1 and T2 times. Okay, so that is what the errors of T1 and T2. Okay, so there is a control line error. Maybe there is a problem with the signal which I have sent, or there is a problem with the signal coming from the circuit that may also cause the problems in the calculation. Okay, right? And one more thing, the next error is, okay, I have a quantum circuit. Before something goes into the quantum circuit register, I start everything in a zero state. This is how quantum circuits are started with. Later, I will have some kind of a gates which prepares as per my requirement quantum superposition. Okay, but even starting itself with some issues is are there, that is going to create the like preparation errors itself. Okay, right? So these are the list of errors which I am going to have in quantum computation or even quantum hardware while working with some tasks. Okay, right? So okay, that is established now. Okay, let's see the types of quantum errors. How can we show on a Bloch sphere? Okay, so on a Bloch sphere, if you just I was showing here, if the quantum state is initially prepared in the ground zero state, okay, due to the noise, due to the other errors, there may be chance 0 become 1, 1 becomes 0. That is called a bit flip error. So it was shown here, the bit or a qubit, part of a quantum qubit, which is pointing towards the north pole, becomes a south pole. Okay, so that is a bit flip error. Another one is something called a phase flip error. What is a phase flip error is, okay, suppose if I have a quantum state which is supposed to be like this, okay, due to some noise, there is a relative positive phase between 0 ket and 1 ket, that becomes a minus. What I mean is, the quantum state becomes a psi prime instead of psi, like this. It becomes like this. So there is a minus sign, the plus sign become a minus sign. Now how can I show it on a Bloch sphere is, let's say my quantum state is equal superposition state, which is like this. Okay. In short, we can write them as a plus gate state. Where it is pointing along the x-axis. If I just take x-axis, now from positive x-axis, it becomes a negative x-axis. Negative x-axis is what? Negative x-axis is plus 0 cat minus 1 divided by 2, square root of 2. Okay. So the phase flip is the relative phase between 0 ket and 1 ket is changing from positive sign to the negative sign. Okay. So that is a phase flip error for you. Okay. So here you see pointing towards the positive y becoming a negative y. Here on the top you can see the quantum qubit pointing toward the z becoming negative side. Okay. There is a other error is called depolarization error. What is this depolarization error is? Let's say I take a let's say a collection of qubits in a box. Okay. All the qubits. Now I presume all of them behave like a quantum state sign. Ideal situation I'm talking about. Okay. And because of the, like say it is inside a box, the ones which are at the boundary may interact at the walls, they may slightly vary. That's like how much vary. Earlier I said 40%, 50-50% is supposed to be equal superposition, but there are at the boundary, they may become the ones at the boundary become psi1, which is like 51% excited. Okay. And 49% ground state. Slightly varied, but that is a different quantum state. So in this case, if such a variations are there, let's say some n different groups of atoms are like become, what I mean is, okay, right? If I have a box, in the box there is a qubits behave like a quantum state psi1, there is a qubits behaves like a psi2, there is a qubits behaves like a psi3, and so on. There is a psi n group. Okay. Now, to earlier, I assume that all of them are behaving alike. Now, what happens? There are, because of the interaction with the surrounding, they become like a different individual groups. Like say in the college or institution, students will group based on the language. They feel that they're comfortable with the same language speaking, or sometimes the reason wise people will separate and form some groups. Okay. Likewise, here the groups are formed. Now, how should I represent them in one shot? How? There is something called density matrix would come and help us. What is density matrix is, if you just take a quantum state, take outer product of the quantum state. As you know, the quantum state is column vector alpha beta and its bray is alpha star beta star. Now you take outer product of quantum state with itself, I'll be getting a matrix. What is this matrix? Matrix is, it is telling me, diagonal elements telling me the probabilities of the quantum state ground and excited, and off diagonals are telling the possible oscillations or possible superposition or possible polarization of the quantum system. Okay. So this is what a quantum density matrix represented by letter rho. Since there are individual groups are formed because of the interaction with the surrounding, what happens now? I can't write them individual quantum states like with the psi1, psi2, so on. So people write with the density matrix as a density matrix total, which is equal to probability of any given atom falling into a particular group, rho 1 plus p2, rho 2, and so on, p3, rho n. Sorry, pn, rho n. What is P1? Pi is a probability to fall into a particular, that is first group. First group. Okay. And what is rho 1? Rho 1 is outer product with psi 1 with psi 1. So in this way, in one shot, I represented the entire group. right? Now this entire group is no more pure quantum system. It is called a mixed quantum system. Okay, for a mixed quantum system, what happens? I will have representation given like here. Rho is, okay, there is a chance of time the rho would remain as rho itself, okay, and with some the remaining probability it becomes identity kind of a matrix. Okay, what is identity kind of a matrix? If I just go here, identity, what is identity matrix? Okay, if rho is supposed to be identity means, okay, identity by 2 na, so there is a half, no polarization. Okay, so hopping is not there, so that is what identity kind of a matrix. Okay, so that was a problem. I don't want just identity, I want to have a nice polarization. Okay, so because of that, what happens, the length of the quantum state, which is supposed to be 1, it is reduced to less than 1. So that is what called a depolarization. Polarization disappearing. The cross terms which were there, this in the density matrix, there is a cross terms, the very, very important polarization terms. These are the ones which ensure the quantum state is existing in a superposition. This would ensure the quantum state are just like a quantum coin being tossed during the flight, it is flipping between 0 and 1. Okay, if not, it becomes like kind of a identity kind of a gate, identity by 2 or state. Okay, so there will be a block vector corresponding to overall rho total. So block vector is psi. Usually for a pure quantum system, psi is a block vector. Okay, for pure quantum system. But for a mixed quantum system like this, there will be a block vector R. I can get the block vector from the density matrix. Okay, I can relate, and that block vector, if you plot, it is falling with the length less than 1. That is what showed here in my presentation. Depolarization, the length is going within the unit sphere. Okay, so these are the basic errors which need to be corrected. So whatever these errors are causing, so those error crossed errors would look like this. Okay, one need to address those errors. Okay, now how do we address those errors? Let's understand how the classical computing people are doing in the first place, the error correction. And then from there, can we do similar to that? We can explore. Okay, right? So if there is any question, let me see. If there is a question by Matthew G, if there is an energy separation between 0 and 1 state, what will be the energy of the system when it is in superposition state? Very good question. Okay, right? So let's talk about the superposition state. So, and let's try to understand your question first. Okay, what is mean by that is, okay, if I have, let's say quantum level itself we talk, or we can take a real level. Okay, in the real world level, for example, let's say I have four-story building, right? So there is a lift. Okay, there is a lift which is going up and down, right? The lift is going up and down. Let's say I'll put one student or one young kid, and I just leave. I'll just observe. At a given point, he can exist in the 0 level, first level, second, and third. Individually, he can go. Okay. Either he can exist in 0 or 1 or 2 or 3. That's all. He can't exist in multiple places at a time because he's a classical object. Okay. Now, by some means, let's say the lift is oscillating between 0 and 1 very, very fast. So fast. Let's say the student is there inside that lift. Okay. If I try to observe from the far, for me, he is like oscillating between 0 and 1 continuously. Okay. Now, the question you ask, where is the location of that boy at a given point? At a given point, I can't give it because he's just, the moment I just try to note down, he is going up, so upwards. So what I will do this time, he is in superposition of 0 and 1. What I will do this time is, I will make some 100 observations. Because why do I make some 100 observation? Okay. For example, there is some label is there of a bus is somewhere. You want to find a bus number which is going to your destination or not. It's bus a bit far, the number is not seen properly. What you do, you try to observe several times carefully, and several times you observe and then you make it in your head based on the several observations. It becomes a statistics now. The same way, you make an observation on the person who is going back and forth. Okay, so let's say you make some 100 observations. Out of 100, it's going nice equal phase. So 50 times is in the state 1, first floor. Another 50 times is in the second floor. Now, coming back to your question, what is the energy, or what is the energy of the system when it is in superposition? I can't specifically say the energy is just 1 or 2. I can't say. It is oscillating between the both. Okay. So if there is any quantum state which is can be represented of oscillation between the both, which is this quantum state, equal superposition between. So if you want, I can write down as, okay, one, I can write down as 1 ket and 2 ket. Okay, so this is the new quantum state, and with which energy this is existing. Now the question is, I can specifically put a energy value for a thing, but he's oscillating with some frequency mu. You multiply 2 pi, it will become angular frequency. You just take a mu and multiply a Planck's constant, you get some energy. You can say that is the energy with which this guy is existing. Or you can represent h cut, which is h by 2 pi, and you just say h cross omega is another way of saying energy. That is the energy corresponding to that oscillation. Okay, when he is strictly in the ground state, his energy is the ground state level energy. When he is strictly in the excited state, his energy is in strictly excited state. When he is hopping between that, so his energy is h omega or h mu. Okay, I hope I answered your question, Matthew. Okay, right? Fine. So yeah, it is like yeah, it is like something which is in the on the table or below the table. Okay, or something which is going up and down onto the table and below to the table, something like that. Okay, fine. So let me please acknowledge, Matthew, if you got the answer. Fine. So let's get back. Okay. Yeah. So how this classical computer people are doing the error correction? They are working with bits. Bits are zeros and ones. They intend to create a 0 bit and they intend to create a 1 bit. Sometimes what happens? 1 becomes 0 and 0 also becomes 1. Right? 0 becomes 1. That is a problem. Okay? 1 becomes 0, 0 becomes 1. So let me put some kind of a probability. Okay, so again Matthew is asking a follow-up question. Let me see what is that. if you get different energies at different time, what about the energy? What about the energy conservation? Okay, very good. It's a very basic physics question. Okay, so the energy conservation is right. And what do you mean by energy conservation? You supply some energy. The energy cannot be destroyed. Okay, it transfers from one means to other means. Okay, and it has overall energy should be same. Okay, it should not be destroyed. So who is giving the energy for this superposition? I have a diagram for you earlier. Okay, you just see this diagram. The pulse is having the energy. How much energy pulse is having? Let's say h omega energy it is having, and that energy is transmitted to the electron which is quietly sitting in the ground state. Okay, it is quietly sitting in the ground state, no energy to that guy. Now this pulse of photon comes and supplies to the energy. How? It is just like take a coin, flip it, just the way I just give a like a torque of flip. Okay, the same way the photon pulse comes and gives the energy. How much energy is given for the coin, that with that much energy it is flipping, it is traveling, doing the oscillations. So the overall energy associated with the entire flip is exactly equal to how much energy is supplied. So the photon energy is converted into superposition. Okay, so please don't see separately 0 and 1. When in superposition they are the single one quantity. Okay, it is just like if I have some yeah, if you can just take a ceiling fan. If the fan is off state, if I just supply the power, depending on the power, rotation and the speed would happen. If I put in a first option like a level 1, it rotates with a very slow. Level 5, it rotates with very high speed because I've given extra lot of energy. Okay, the same way the conservation of energy here is amount of energy taken or given by the photon pulse is converted into the hopping or oscillations of the electron being doing oscillations between 0 and 1. Okay, I hope you understand now. Okay, coming back again. Okay, this the classical computer people, what they do is they associate a probability for a bit being flipped from 1 to 0 and 0 to 1, because there are binary system. If there is a flipping happening, 0 is becoming 1 means obviously 1 is becoming 0. Okay, so they associate a probability and they will say with the probability 1 minus p, the bit would remain the same. Very good, right? So this is a Markovian technique. Okay, right? Fine, Markovian mathematical model. Now they figure it out exactly where the bits are flipping or the which location bits are flipping with respect to which quantum circuit or sorry, classical circuit bits are flipping, and they think that we need to address it. What they do, they know that there is a location bit may be compromised. What they do, they just clone one bit into 3 bits. Okay, one bit into 3 bit they will clone, and one bit 0 bit into 3 0 bits, 1 bit into 3 1 bits they will clone. Okay, so the idea of cloning by this way is they know that if this, they call it as a 3 bits as a logical 0. Okay, logical 0, right? And this triple one is called logical 1. Okay, now they will send this or 3 guys through the same gate. They know that that gate can only induce a flipping for only 1 bit. So now triple zeros are going along. Let's say the one of them becomes, instead of triple zero, one of them becomes 1. Similar story for triple one. The triple one going through the same gate, so one of them gets flipped to 0. Now what they do, whatever is the output, they'll just assess the output. If as per the democracy, majority. Okay, so there are two zeros, which means 0 0 0, sorry, 0 0. Okay, 0 0 1 is equal to 0, they conclude, because there are two zeros, so they will conclude. So majority even here applies. Okay, this is equal to 1. So this is also called logical 0, logical 1. Okay, this is how you can just do a cloning in classical computing and do as much as you want communication. You just realize there are two bits can be compromised, which means I have to prepare 5 cloned logical bit. Okay, so what I mean is, if there is a chance of two are going to be compromised, so my logical 0 would be having 0 0 0 0 0. This is what, even if two of them just error, two of them becomes flip. So as per my majority, it is actually 0. Okay, so only problem here in this case is, if I presume that only one bit is flipping, so if only the system is only flipping one bit, fine, my strategy will work. I presume that only two qubits are flipping, okay, and I do the strategy of this cloning, my strategy will work. Let's say I presume something, the system does something. Okay, I presume there are only two qubits, like one bit is flipping, but there are two bits are flipping. Okay, my assumption is wrong or my observation is wrong. Okay, in that case, what happens? Let's say three zeros, instead of being three zeros, they become two ones and 1 0, like this. Okay, now what is as per majority context? This is equal to 1, this is equal to 0. So which is exactly opposite. I intend to send a 0 on the top, 1 on the bottom, but it goes other way around. So there is a problem. What is that problem is, the system, whatever assumptions you are making or whatever some strategy you are planning, the system should behave as per the strategy. Otherwise, you are going to end up with trouble. That is what showed here. Okay, so if there are three qubits, or sorry, three bits are there is a chance of one bit flipping is represented by probability p. 1 minus p is the flipping probability. So 1 minus p is the retaining the system in the same state. P is the flipping probability. Among the three, if two bits are flipping, in that case, what is the probability of error is shown here. Okay, just by simple probability and statistics method, you can show that this expression corresponding to error probability in the case of 3 bits, right? So among this, if any given bit is flipping with a less than half a percentage of probability, then I am fine. If it becomes more than half, then I will end up in trouble, because more than half p means, p is more than half means, or equal to half means, immediately what happens? The probability of errors goes into the heaven. Okay, so that means all my calculations go wrong. So these classical computer scientists have to keep in mind, whatever the assumption or whatever initial situation they are taking, that should work. Okay, fine. Let's say we will also make the same strategy, and we'll ensure that there is a one qubit which is going to be compromised in a location, and we think that, or we assume that only one qubit is compromising. Okay, right? So in that case, what we can do as a classical error correction? Okay, I'll conclude for after I will conclude now for within 5 minutes. After that, we can take a quick short break. Okay, so Is it possible for us to replicate the same error correction in a quantum computation? Yes or no? The answer is straight away no to some extent, yes for some extent. It's a very interesting. Again, it is a superposition of yes and no. What I mean is, okay, right? So in quantum computation, there is no cloning. I can't clone 0 bit to multiple qubits, 1 qubit to multiple qubits. I can't clone. Okay, that is one hurdle. Number two is the errors are occurring continuously. It's not like in a classical computation, one place there are errors are occurring, you address them, fine. But in quantum computation, you are addressing error in one location, another location errors are also parallelly occurring. So you can't go hopping between the error locations and correcting it. So the errors are happening continuously. So straight away, like replicating classical error correction is not possible. Okay. And one more problem is to know whether the error is occurred or not. I want to make an observation. I want to find. So for that, where is the error location I want to find, right? I have to make a measurement. But such a measurement, you can't do it here in classic quantum computation because every measurement destroys the quantum information. You see, it is like a coin being tossed. Whether to see what is it, it's a coin. It's a coin from India, or it's a coin from some other country, Western country, or US or UK. You need to catch and see it. When you try to catch and see it, what happens? You are actually disturbing quantum nature, superposition state. So after that, there is no chance you can put that back into quantum superposition state because you have destroyed that quantum state in the first place. Okay, right? So that is what you can't, without observing a system, without making a measurement, you can't know about the insights of the system unless you use a very advanced readout technique methods. Okay, so straight away you can't implement the same error correction in classical computing into the quantum. But what you can do, you can take the inference, you can take the idea, right? You can just use as an inspiration and come up with a new technique of doing error correction in quantum computation. What is that is, okay, it is called quantum encoding. Okay, so what is the quantum encoding is, just let's take a superposition state. Okay, this is a superposition state. Okay, 0 bit is there, 1 bit is there. Okay, if there is a quantum state is there, psi. Okay, so if I straight away follow the classical computation, what I should do, I have to convert that psi into 3 psis clones. Okay, that is not possible. So what you can do, you can do an inspirational type. What is that is, instead of having quantum state alpha A0 ket, B1 ket, I can create A000, B111. So this is also of same superposition. You see, both are of same superposition. Only the basis elements are different. That's all. Basis on which it is constructed. The basis on which it is constructed is 0, 1 base. Basis on which it is constructed is 0, 0, 0, 1, 1, 1. Okay. So it's a base of 3 qubit system. This is a base of 1 qubit system. Okay. Right. What are those 0, 0, 1, 1, 1, 0, and so on? There are 8 elements. So that is what the quantum base state is. Quantum base state, the new base state is this, old base state is this. Okay, if you do that, you can do the error correction. Okay, so we'll just take a quick break. How is this encoding is done using quantum circuits? We will see, and then we will follow it up further the quantum error correction. Okay, right? So we'll have a stop at this point exactly 3 o'clock. We'll take a 5 minutes break. 3:05 we'll start.